So what would be the brute force way to do this? Well, the brute force way to do this is to consider how do we generate solutions that are valid and what is going to be the smallest such solution. Well, so let's suppose that your change, the total change you need to give is n cents. So there is the simplest solution that will not be optimal, right? Which is n of 1 cent, right? So that means that you can just return n coins, each one is 1 cent. In this case, your solution has n coins. And that, could be a lot of coins, right? So you want to see whether or not you can reduce this number of coins. In that case, then you can do it by asking yourself, can I now find a solution of n minus 1? So I can try to find a solution of n minus 1. Well, in this case, I can't really find a solution of n minus 1. I can find a solution of n minus 2. Now at some point, I'll be able to find a solution of n minus 4 coins. So how do we get n minus 4 coins? Basically, I get n minus 5 of 1 cent coins, and I get 1 coin that has 5 cents. So in that case, I'm going to get an answer that is n minus 4. Then you ask, can I now get an answer that is n minus 5, n minus 6, n minus 7? So each time you try to reduce this, and at some point, once you can no longer reduce the answers further, then you are going to arrive at the brute force solution. Essentially, to try all possible solutions and see how big they are. Now, the greedy solution is pretty intuitive, pretty straightforward. So we're just going to start from the biggest coin, because that's going to be the one that pays off the most. So we have 35 cents here. So we have 20 cent coin, which is the largest. So then we can do that thing, right? So for example, while n is greater than 20 cent, then I can reduce 20 cent away from n. And then while n is greater than 10 cents, I can reduce away 10 cents. While n is greater than 5 cents, then I can take away anything that is 5 cents. And finally, when everything else is already done, for as long as my n is still at least 1 cent, so I'm going to take away 1 cent. Now in this case, we just need to increment the number of times that we go inside the while loop. Then we're going to have a number of coins that we are returning based on the greedy solution. Now for 4C, for the above coin denominations, is there any change amount for which greedy fails to find the optimal solution? So it turns out that for this case, the answer is no, because the greedy algorithm, because of the coin denominations, we cannot have any combination of the smaller coin denominations that would still get us a fewer coins than just simply using the bigger coin. So for example, can I do better than using 1 20-cent coins? Well, it turns out that I really can't, because for anything that I can cover with 20 cents, I cannot cover it with any smaller combination of 10, 5, and 1. They will still have fewer coins. So in that case, the greedy algorithm also happens to be the optimal one. So in this case, the answer is the greedy will never fail to find the optimal solution for these coin denominations. Alright? So this is just another example of the greedy